Okay, now I'm going to introduce this idea of coupled reactions and reactions moving towards or progressing towards equilibrium, which we know that they do because the second law of thermodynamics dictates everything that we do. So I have the reaction A goes to B, and there's a rate constant K sub R. I also have the reaction B goes to A, and I'm going to say that its rate constant is Kr prime. So I can say that the rate equals Kr times the concentration of A, and in this case, the rate is equal to Kr prime times the concentration of B. Hopefully you all follow that. And when you're depicting a rate law, that is the rate constant multiplied by the concentration of the reactants. Okay, so if there are two, it would be A times A. And if this was, it would be Kr A squared. Okay, so equilibrium is defined as the rate of the forward reaction, or actually, let me say this again, or rewrite this. If I write this as A goes to B, but B can also go back to A, I can write it this way, such that I have an equilibrium or a directional, or both directions of the reaction are occurring. A is going to B and B is going to A with Kr and Kr prime. Okay, if we then say that the rates of these two reactions, or the rate of the forward reaction, is equal to the rate of the reverse reaction, we have an equilibrium. So if these two rates are equal, equilibrium occurs when the rates are equal. And I will emphasize the rates, not the rate constant. Easy trap to fall into. You'll be like, oh, the rate constants are the same. We must be in equilibrium. Rate constants have nothing to do with equilibrium. It tells you where equilibrium might lie, kind of, but it has nothing to do with defining equilibrium. That's when the rates are equal to one another. Okay, so if we set these two equal to one another, I've got Kr times the concentration of A is equal to Kr prime times the concentration of B. Something that's cool though, I can rearrange this to say, well, if I look at the ratio of my two rate constants, that becomes the concentration of B divided by the concentration of A. Does that look familiar? Yay! The equilibrium constant. So the ratio of the rate constants for the forward and the reverse reaction for this system is equal to the equilibrium constant based on the ratio of the products to the reactants, or the concentrations. I should emphasize that this would actually be the activities. And so we are assuming that the activity coefficients are equal to 1 for these concentration reactions, but I digress. Okay, so that's how we establish equilibrium. Sound cool? Yay! So there's our equilibrium constant, and I'll get rid of those since it's not a factorial. Okay, so let's now look at what this means in terms of the dynamics of getting to this equilibrium. Okay, so I have concentration plotted as a function of time with A going to B. So you can think about this as if we first start with a low concentration of A, and then we've got a high concentration of B. Let's actually, no, sorry, that's a bit backwards. Okay, and let's just go this way. So A goes to B. So we start off with not much B. So it's going to start pretty low. And then there's going to be some increase in the amount of B until it levels off. Cool. Likewise, and actually, I'll start here. So then I can say, well, I'm going to decrease the amount of A that I've got, and then it's going to turn into some amount of B. Okay, so I'm going to lose some of the A. And I moved it down just because we're not guaranteed that the concentrations would be the same, that B would become the concentration of A. Okay, so this would be the initial concentration of A at time 0. This would be the initial concentration of B, and there's this gradual change, or steep change, depending on the reaction, to where then you get to where dA dt and dB dt are both equal to 0, i.e., the reaction has reached an equilibrium. The change of the concentration of A is now 0. It's not that the concentration of A is 0, it's the rate at which it is changing is 0, which means we have reached an equilibrium between the two. Okay, so we want to know then, how do we describe or define mathematically this portion, getting towards equilibrium? Sound good? Let me clarify that. So we're going to try and create an equation that's going to take into account both the consumption of A and the formation of B while taking into account the consumption of B and the formation of A. We're going to combine these two together. Okay, so let's do this. So I have minus dA dt is equal to, so we're going to have is equal to the rate law of A. So this is the formation of A, or sorry, this is the loss of A from Kr prime from the forward reaction. So I'm losing A from the forward reaction, but I'm gaining A from the reverse reaction because B is turning back into A. So I'm going to add Kr prime times the concentration of B. Sound good? So I've lost A, and this is representing the loss of A, as in the rate of consumption of A, and this is representing the gain of A. Okay? All right. So this whole thing is the net change of A. All right. Such that now we have to take into account, well, how do we quantify then what this function would be in terms of A? So again, the goal is to find A as a function of T. Okay, so A, so the concentration as function of T. So just like before, when we were determining the integrated rate laws, we were wanting to find the concentration as a function of time, but now we're coupling the forward reaction and the reverse reaction. We've complicated things. So now we want to find A as a function of time. Cool. Game plan. I'm going to show you how to do this fully, i.e. from solving the differential equation, which is hidden right here, where I'm going to move this over and it's going to become 0 is equal to dA dt plus KRA plus Kr prime B. And then we're going to solve that differential equation and then get a result. Next, later on in the chapter, you're going to find that there are ways to approximate doing that. So we're not actually going to do this solution or solving the differential equation for all of the future problems, but it's important for you to know how it works such that you then know when you can apply the appropriate simplification to solve this type of problem. Cool? Let's do it. Okay, so here's our equation. Minus dA dt is equal to Kra minus Kr prime B. So the same idea at T0, we know that the concentration of A is equal to A0, and we're going to assume that we're starting with 0B. That just makes things easier. Let the system go towards, so we're starting with some concentration of A, and let it decrease such that you're starting with 0B, and then let that increase. And it's just a nice way to quantify the system. You can start with some B, that'd be cool, but that's a little bit more complicated. You're on your own if you do that. Always start with the simplest problem, if you can. And if you can't, simplify it till it becomes the simplest problem. Oh, PChem can teach you so much about life. All right, where the hell was I? Okay, so T0, we've got this, and then at some later time t, A is equal to some A0 minus X, and that means that B is equal to X. Isn't this cool that the same approach that we took to solve the integrated rate law can be used here? We can also say, or the concentration of A plus the concentration of B at any given time is the concentration of A0. Cool. So if you combine those two, that means that you're going to get A0. Or you can then say B is equal to A0 minus the concentration of A at any particular point. Go team. Okay, so let's go back to now incorporating this relationship Actually, I think I'm going to use this relationship into there. So minus dA dt is equal to Kr times concentration of A, which is here, A0 minus X, minus Kr prime times what is B? B is just X. Cool. Or I can say, instead of X, I can say is equal to A0 minus A. Awesome. But then I can also say that A, so this is Kr A0 minus X minus Kr prime times A0 minus quantity A0 minus X, but there's a negative sign here, so this is going to be plus X. Cool. Which is the same thing as just saying that it's X. All right. Everyone follow? This is the approach. Now we have this, and we can solve for what X would be. And then, so we solve for what X would be. We can convert this A into an X by saying this is dA0 minus X. And so then we now have a dx dt, and we have X's over here, and we would then integrate and determine what that X function would be. Lots of work. Or I can just skip to the solution, because again, this isn't a mathematics class. We would use the solutions to the differential equation to then build on understanding our chemical system. So again, what we're doing is we're finding A as a function of T, how it's changing. Oops, sorry, it's this part. We're wanting to find this part, a function that describes that decomposition, as we have an included formation of A because of the equilibrium, or because of the reverse reaction. So solving the differential equation that I set up before, you get Kr prime plus Kr times exponential to the minus quantity Kr plus Kr prime, multiply that by time, divided by quantity Kr prime plus Kr, all of that multiplied by A0. Cool. We don't need to go through solving that. If you can, if you want to, God bless, go for it. But what we can do is we can say, all right, I know what this now solution is, and if dA dt equals 0, groovy, we're at equilibrium. So we can solve for the equilibrium concentration. And again, these are the equilibrium concentrations, such that either you know where when you reach equilibrium, or you can get to where you have a, well, so you know what these are going to be when you do get to equilibrium, depending on your starting conditions. Okay, so I have listed, you can follow the example in Atkins on page 737 for the 11th edition. So if you solve for these equilibrium conditions, you get A equilibrium is equal to Kr prime concentration of A initial divided by Kr prime plus Kr, and then the concentration of B at equilibrium is equal to Kr times initial concentration of A divided by Kr prime plus Kr. Okay, so notice now that the initial concentration of A dictates both the equilibrium concentrations of A and B, but they also depend on the combination of Kr prime, and Kr, Kr prime, and Kr. Notice how you've got Kr prime here and Kr here. There's the difference there. So if you want to then, let's see, where am I going next? Cool. So the goal of all of this, let's take it back, big step. Why are we doing all of this? The goal is to find expressions for the concentrations of A in terms of the rate constants of the different steps. Okay, so the goal and I should have said there was a 1, which was solve the differential equation. 2, this is solve for equilibrium concentrations. So that's step 1 and step 2. Okay, so the overall goal of this is to find the concentration of A or the concentration of B in terms of Kr and Kr prime. All right, we want to find those expressions because when you have coupled reactions, this can simplify into the effective rate constant, which is going to be some sort of rate is equal to K effective times the concentration of A, where this K effective can then be broken down into Kr prime and Kr, or Kr and Kr prime. Okay, so that's the overall goal. Because what it can do is it can then give us insight into how this process is going to dictate when, which is this time here, equilibrium occurs. Cool. This process right here is called the relaxation. And there's a relaxation time associated with the time of beginning the reaction or perturbing it out of equilibrium and it returning to equilibrium. Is known as the relaxation time. And now let's get into what that would be. Okay, so let's assume that we've got A and B with Kr and Kr prime. Again, Kr being the rate constant of the forward reaction, Kr prime being the rate constant of the reverse reaction. And at some temperature, or finally at temperature, T1, we're at equilibrium. Okay, and then all of a sudden you turn on the heater. Let's assume that here's my little PChem candle. So I'm adding heat energy. That's going to affect the equilibrium constant, Le Chatelier's principle. That's going to perturb the system, which means now that the new equilibrium, say, is way up here, we're shifting it such that we favor the reactant side. And so there's going to be a increase, whoops, here, such that now we've reached a new equilibrium. This is a way to look at the relaxation times. And so the change in the equilibrium position because of the change in this temperature is going to change or adjust the where equilibrium is going to lie. So if you increase the thermal energy in the system, that might make the reaction this way much more favored, such that you're going to be increasing the concentration of A. And so by changing time, so a delta T such that T2 is greater than T1, you're going to be affecting equilibrium by that delta T. And so what you would do is you would then solve the differential equation associated with the time of this return to. So you'd solve what is the function that gives you this curve, okay? And you would then solve what that equation would be. And I am going to, so solve for A as a function of time to satisfy this relaxation condition. Okay. Now, the only reason I'm doing it this way is because I don't really care that you can solve it. I want you to be able to interpret the results. Wait till grad school to solve for it. They are fun, I promise. So the solution where X, so A, is equal to some equilibrium concentration plus X, because we're adding A back, and then B, the concentration of B at any given time, is equal to the equilibrium concentration minus some X value. And so then you would solve for the differential equation. So dA dt is going to be minus Kr, concentration of A, plus Kr prime, concentration of B, and that's going to be equal to a minus Kr plus Kr prime, quantity that, times X. I don't care that you can set this up or solve for it. I want you to appreciate where it's coming from. Okay, so the goal is to find the function that satisfies this equation, and we find that function, that x is equal to x0 e to the minus t over tau. What the hell is tau? Okay, so first of all, don't worry about what the x and x0 are. They can be related. Well, I mean, you can. So x is equal to the difference between a and a. So x is equal to a minus a at equilibrium. Solve that from here. And then this tau is equal to the, oops. So my taus are weird. Should look something like that, maybe. I kind of do this funky T, whatever. So this is known as the relaxation time. Okay, and that relaxation time is the time associated with the relaxation to get back to equilibrium. And it can be related to the rate constant, where, poor use of board space, where 1 over tau, whoops, is equal to Kr plus Kr prime for this particular example. This isn't always true, but the rate constant is related to the relaxation time. And typically you just take 1 over the relaxation time to get the rate constant. That would be the effective rate constant. Cool. Okay, I think that's all I want to talk about with relaxation times and relaxation. This, if you are going on into graduate school in chemistry, in particular, physical, organic, or any organic work, knowing relaxation times is really important because it gives you insight into kind of the time associated with the actual mechanism occurring. I've done significant amount of work in a modified transition state theory that's looking at applying transition state theory, which we'll get to later in this chapter, but it's applying it to transport properties. So molecules diffusing through a material, the viscosity, the momentum transferring through a material, conductivity, the charges migrating through a solution. And the relaxation time has been incredibly useful. And I study what's called a dielectric relaxation time. So if you have these molecules and they're oriented in certain ways, you expose them to electric field, they're going to orient themselves in a non-random assortment, or an assortment that's not dictated by just the local environment. It's going to be affected by the external electric field. So there's a relaxation time associated with you hit them with this magnetic or electric field, and then they respond back to an equilibrium. And so you can learn a lot by watching the relaxation of perturbing the system at one system, so one condition, do something, change the system, and watch it go back. Relaxation times are very, I mean, this the way that we use NMR. You're looking at the relaxation of the magnetic dipole, well, the oscillating magnetic dipole, which is then converted to a Larmor frequency. So you're watching the Larmor frequency respond back after being perturbed in some way by various radio frequency pulses. So relaxation time chemistry, or I should say relaxation physics, is really important when you're looking at non-equilibrium dynamics, which of course are going to equilibrium. Thank you, second law. Cool. Anyway, but that's where relaxation times come in. Bonus. Bye.